Getting to garbage collection, pathological cases for a class of reachability-based garbage collectors. And this presentation is by Matthew Sotoudeh.
Sotoudeh, yes, let's say that. I'll ask my dad at some point how he likes pronouncing it. Okay, so I guess we're going to shift gears here a little bit and talk about garbage collections. You're in the proof section. There will be a proof at some point in this paper, so look forward to that. I'll spend a little bit of time here telling you why I care about garbage collection. Well, you know, memory management is a big problem. Anytime you have a program that's long running and you use memory, you're going to need a story for memory management. So every language out there, almost every language has some story for this. I like to sort of categorize a lot of the common memory management, styles in this triangle of trade-offs. Right? So the classic one is just manual memory management, like C. This is very permissive. You can write doubly linked lists, which is great. I love them. And you can get like good worst case performance if you do it right. But of course, there's the never-ending safety problem. So this does not spark joy. Next, there's Rust, right? Or the static typing strategy. This has safety, modulo all the bugs in the Rust type system. And it gives you, just like C, sort of good worst case performance because it's happening statically. But of course, you can't write your doubly linked lists. And in general, the whole mantra of the type system is to restrict the programmer, right? And that also does not spark joy. Finally, we get to garbage collection, which you might think of as like the Java approach to things. And this is having permissiveness. You can write doubly linked lists. Apparently that's my goal in life here. And you have safety, but you miss out on the worst case performance. And there's going to be some garbage collection people out in the audience that are going to tell me that, but in the average case, it's actually better performance than C or whatever. That's all true. But I have actually run into the worst case performance, thrashing issues in garbage collectors in practice. So it would be really, it's not perfect in my mind. There's still a trade-off here. Okay, so the key question in this paper is we're going to say, can we reach perfection? Could someone someday invent a garbage collection algorithm that really achieves all perfect permissiveness, safety, and performance, even in really pathological scenarios, like where the heap has cycles in it and you're operating close to the memory limit? That's the kind of philosophical question I want to get an answer to. And I did get an answer. There's some caveats that we'll go through, so take everything with a grain of salt. But the answer is basically no. This is not a surprising answer, which again, we'll get to the caveats. But it's a no, even if some crazy new graph algorithm is discovered, right? Like even some kind of, there's the Euler cycles, there's the vertice degree 2 and everything. Even if there's some crazy new graph theory stuff that's discovered, the answer is still no. We're not going to be able to achieve this perfection. It's still no, even if the garbage collector gets to use some unlimited amount of side metadata memory. It's a fairly strong no. And this no is proved in the paper with mathematical certainty and precision. It's not just like I sat down and thought about what does mark and sweep does. It's really like a mathematical proof about all algorithms for a certain class of algorithms, as we'll talk about. So let me tell you what these sorts of difficult cases look like for current garbage collectors, right? Like you can think of mark and sweep or concurrent mark and sweep and so forth. Like what are the sorts of issues that I run into sometimes and get annoyed at? And it's kind of called thrashing. So imagine you start up your program, you allocate a bunch of regions. Okay? You call alloc a billion times and you fill up your whole memory. Your memory is filled to the brim. Okay? Then you make a bunch of pointers among these regions. Okay, I don't know how you make pointers. You just make a bunch of cycles and everything in there. There's some bunch of pointer relations here. Then you manipulate the pointers so that one of these regions becomes unreachable. You no longer need that region anymore. So in theory, it could be collected and reused by the garbage collector. And then you ask for a new piece of memory. Okay, you ask for a new allocation. And at this point, the garbage collector or the program runtime system has basically two options. First option is that it can actually go through and prove that that region is unreachable, prove that there is space you can reuse for the new allocation, and collect it and then reuse it and give it back to you when you call alloc, or it can just say, I'm out of memory, right? And so the second one is not desirable. It does not spark joy, again. So we always want to be in the first one as much as possible. And sort of the proof in this paper is showing that no garbage collector in our formal model of garbage collection can sort of consistently achieve this number one option here. of like actually realizing quickly that something has become unreachable without introducing like, unreasonably long pause times. And this is really crucially dependent on like what pointer manipulations you make here, right? Like if your pointer manipulations never insert cycles, you can do rough counting and it's fine, right? But the proof here is basically that there are some pointer manipulations that no matter what crazy graph algorithm you have, it's not going to be able to determine quickly enough that that region was unreachable. So this is just a little bit more about that. Yeah, so clear that like classic tracing algorithms suffer from this. If you ask garbage collection researchers, they're going to tell you, yes, this is what we expect. We don't expect that somebody's going to come up with some crazy new algorithm. But in graph algorithms, there are surprising algorithms. When I first learned about that Euler cycle thing, it surprised me, right? And so am I going to be surprised in 10 years that one of you comes up with some incredible new, worst case performance garbage collection algorithm? That's kind of the question here, right? So how do we kind of rule that out with mathematical certainty, even for algorithms not yet invented, even for graph theory facts not yet discovered, that all of those algorithms will fall victim to some pathological example like this? That's really the motivation for this talk. And if you're like me and you've taken some intro undergrad required computability or complexity theory course, you know the easiest way to do this is just to reduce to somebody else's hard work. Okay, and that is basically exactly what I did here. So I showed that if you have an unbelievably good garbage collector, that would mean that you could take that unbelievably good garbage collector and use it as like a subroutine to make an unbelievably good dynamic connectivity data structure. And this should actually say reachability, but whatever. Okay, so it's going to be a straight up reduction. I'm going to show you a straight up reduction in the next few slides. But first, let's pause and talk about some caveats here. These proofs are specifically about the worst case, not the average case. In order to prove things, I can't just talk about garbage collection, because garbage collection is kind of an informal concept. Do I mean, copying collectors? Do I mean in-place, so forth, right? So on the next slide and in the paper, I'm going to give you a more rigorous definition of what we mean, right? And the proofs are only going to apply to algorithms that can implement this garbage collection data structure interface that I have in the paper and then I'm going to write down on the next slide. So if your algorithm is not general enough to implement this interface, then our results don't apply to it, and you've successfully evaded this. Of course, heuristics can improve the average case. We're talking about the worst case. And language restrictions like type system restrictions can sidestep even in the worst case. But then in that setting, your collector just doesn't need to be general enough to implement the GCDS interface. I'm also going to be loose with the notion of running time here. See the paper if you really want. There's like a 20-page appendix. It's all written out there. Okay. So for the purpose of this project, what I mean by garbage collector is formalized in this kind of interface here. Okay, so you can, I won't go through this too much, but you can allocate regions, you can insert edges or pointers, delete edges or pointers in the heap. We kind of try to model concurrent collection by saying you can give the garbage collector, tell it just do one time step worth of work. And the main goal of the garbage collector is to put things on this free list once they've become unreachable. Okay, so you can see the paper for more details about this, but just keep in mind there's a formal model behind all of this of what precisely we mean by garbage collector in this setting. That is really everything and the only thing that our results apply to. So what do we reduce from, I think is the direction here. We reduce from this dynamic connectivity data structure. Actually, today I realized I've been doing this wrong. I should say reachability. The graph theory people are opinionated about connectivity being for undirected and reachability for being for directed, but I don't care that much. Basically, this is a much simpler data structure. So here you imagine you're storing a graph. The user of the data structure can add edges, they can remove edges, and they can ask, is there a path from this node to this node? Okay, that's the data structure. The graph theory people care about this data structure, or the graph algorithms people care about this data structure, and they care about proving that this is a hard thing to implement super quickly. Okay? You may notice it's very similar to the garbage collection data structure interface, and that's basically what we're taking advantage of. So I'll go through, hopefully quickly, how this reduction works, just to give you a sense. We're going to mirror the sort of graph thing that the dynamic connectivity interface cares about inside the garbage collector's view of the heap. Okay? So if the user of the dynamic connectivity data structure says to add an edge, we're going to add the corresponding edge in the, the garbage collection world in the heap. And if they say delete an edge, we're going to delete the corresponding edge in the heap world. And everything else is, so that's all basically the same. One thing to notice is that in the garbage collection world, we've introduced this special sort of pseudo root node X that connects to everyone else, and it's connected to by the root, meaning the stack and globals and locals and so forth. And so now the question is, what happens when the user asks in the connectivity world whether there's a path between D and C? And so you may have to just kind of take my word for it, but what you should do is this. You should sort of send some water flowing from the root to the source, D, and then disconnect X. Okay, so X was all of these guys' lifeline to root, but now the lifeline goes through D. If it can reach the destination C, then you're going to add a back edge from C back to X. And so if there was a path from D to C, then nothing becomes unreachable here. And so the nothing becoming unreachable in the garbage collection world means nothing gets added to the free list. And so that nothing being added to the free list will tell you that actually those were connected. You can walk through and convince yourself that the sort of converse works out the way that it should. And again, I'm being loosey-goosey here with some things. See the paper for details. Okay, so what have we shown? If you had a really great garbage collector in this sense, then you could make a really great dynamic connectivity algorithm. And in particular, like the speed at which the garbage collector realizes that something is unreachable corresponds to the speed at which you can answer the dynamic connectivity query. But these super smart guys, Larson and Yu, showed that actually it's not possible to have a super fast dynamic connectivity algorithm. Right now, they're only at super logarithmic, was like a huge deal in 2023 when they got to log 3/2. But this is like, it is conjectured that it's up to n or n squared or whatever mark and sweep would be. So this is like a super active area of research in their community. And these results actually basically connect these two things. So we have reductions in both directions, so they're essentially the equivalent problems. Okay, so it's cool to have that kind of bridge here. Thanks. Yeah, so just quick additional results. There's always been this question about, can you add cycle collection to reference counting? And so there have been attempts, and basically we prove here that the answer is no. Actually, you sort of can't without also slowing down the program for some pathological acyclic program, which is sort of surprising. So it's hard to determine when you should switch from ref counting to garbage collection, and provably hard. But we do have an algorithm that does this in the sort of optimal sense, for some sense of optimal. See the paper or ask me afterwards for that. So here's a summary of the stuff. I just wanted to say a quick thank you to the anonymous reviewers. I was sort of maybe a belligerent author in some of the review and feedback portions, but I think the paper really was improved greatly with their feedback. So thank you so much if you're in the audience. But I'll take questions now for however much time we have left.
Right, thank you.
So the problem you're reducing to, you said it's big omega is log 3/2. What's the big O on that currently?
Oh, of the actual algorithm. I believe so these things become difficult about whether you're counting like nodes or edges, but it's like O of n or O of n squared. I think the best algorithm they have is actually the equivalent of mark and sweep.
Okay,
I don't think they have any smart algorithms.
Is the current speculation that it will not stay logarithmic? Because if it's logarithmic, on modern computers, logarithm is actually constant. It's 32 or
No. The speculation
nowadays.
is that somebody someday will prove a lower bound that's like omega n or omega n squared. Yes, and there's a conjecture called the online matrix vector multiplication conjecture that actually implies this is true. So and implies a lot of related problems are also hard. So it's kind of their equivalent of SAT being hard. So the conjecture is really that mark and sweep is the best you can do in this sense. And they believe that too, and they're trying to prove it. Yeah.
Okay.
Cool, thanks.
All right, thank you again.